A random variable is a variable whose outcomes are both numerical and the result of a random phenomenon. A discrete random variable is one that can only have very specific values, rather than a continuous stream of values. Examples of a discrete random variable would be maybe the number of children a couple can have, or the number of defective crayons in a box of 8. So in this video, we're going to explore how to analyze a discrete random variable by constructing a probability tree, creating a distribution table, and calculating the expected value. Let's say we're interested in playing a carnival game. The rules are this. You roll a fair 6-sided die, and if your number is even, you get to pick one card from a deck of 5, each containing a unique number from 1 through 5. Then, depending on the number on your card, you get to win that number of tickets. So, if you pick a card that has a 4 on it, you get to win 4 tickets. And let's also say that to play the game, you have to pay 2 tickets. So to explore your outcomes and their respective probabilities, let's construct a probability tree. We start with the first part of the game. When we roll a fair 6-sided die, we have 3 possible outcomes that are even and 3 possible outcomes that are odd, and each have an equal opportunity of happening. So this means really we have 2 distinct outcomes, even or odd, and each has a 3 out of 6 chance. So simplified, this means that we have a 1 out of 2 chance of rolling an even number and a 1 out of 2 chance of rolling an odd number. If we roll an odd number, we lose and we have to walk away. So overall, since it costs us 2 tickets to play, we're down those 2 tickets, and we write -2 as our outcome. Here, let's stop and define our discrete random variable x. We're going to define it as the number of tickets earned playing the game. So since it costs 2 tickets to play the game, and we didn't win any tickets, we earned -2 tickets. In other words, we lost 2 tickets, and that's where that negative comes in. So we know what happens when we roll an odd. What happens if we roll an even? Well, we get to move on. So next we pick a card, and we have 5 possible outcomes here, each with an equal opportunity, and each with a 1 out of 5 chance. So each of the 5 outcomes results in a different number of tickets, and we write them here. So if we pull a 1, we win 1 ticket, but since we paid 2, we're actually still down 1, and we're going to write a -1 here. And then if we win 2 tickets, we break even. If we win 3, we're up 1. If we win 4, we're up 2, and if we win 5, we're up 3. And our probability tree is done. So now we're going to organize all of this information in a table. A probability distribution table has 2 rows, usually. Each possible outcome is on the first row, and the probability of each outcome occurring goes on the second row. So what are our possible outcomes? And there we go to our tree. So we can lose 2, which we wrote as -2, lose 1, break even, win 1, win 2, or win 3. And this is why we call this variable a discrete random variable, because these are the only options, so they're discrete options. We know exactly what they are. There's no in-between options. There's no infinite number of options. These are them. So to find the probabilities of each of these outcomes occurring, we simply start at the beginning of the tree and multiply our way across. For example, to lose 1 ticket, we first have to roll an even, which is a 1 out of 2 probability, and then we have to pick the card that only says 1 on it, which is a 1 out of 5 probability. So 1 out of 2 times 1 out of 5 is 1 out of 10. Overall, we have the probability of 1 out of 10 to lose 1 ticket. So we can do this for each outcome and then place those values in the table. And now that we're done, let's check that this is an appropriate probability model. Do all of the probabilities add up to 1? They do. So we must have done something right. So now that we have our distribution in a neat table, what does it tell us? Well, as a player, we now know that it's more probable to lose than to win, so maybe we should just walk away. But as with most carnival games, that is always true. So sometimes you just want to weigh one game versus another and see which has a higher probability of winning. So this may actually have a pretty good probability for us compared to the other games. Now, let's turn the table for a second. What if we're the operator of the game? If a lot of people played our game, would we expect to win a lot of tickets? Would this be profitable for us? Because we do have to pay the guy to sit there. We have to rent the space. Is this going to win us enough ticket to cover our costs and then earn a profit? So you can imagine if you were a casino owner and the tickets were really dollars, this would be a very important question. So to do this, we find what's called the expected value of our discrete random variable. And an expected value is a long-run average value of our discrete random variable. In other words, this is the average number of tickets, won or lost, per player if a lot of players played our game. One way that you can think of an expected value is that it's a weighted average of all possible outcomes. And we weight each outcome based on their respective probabilities. Since we have a smaller chance of a player winning 3 tickets than losing 2 tickets, we have to weight that outcome of winning 3 tickets less than the outcome of losing 2 tickets. Computationally, we simply just multiply each outcome value, being careful to keep the negatives and positives organized, by its respective probability, and then add each of these components to come up with our final average, our weighted average, or our expected value. So here we see that our expected value is negative 0.5. This means that on average, if a lot of players play our game, on average they will lose about a half a ticket. This means that as an operator, we will win on average a half a ticket per player. So our goal as an operator would be to get as many players as possible to play in a small amount of time, because then we'll win more tickets. So if we had 100 players play our game, we would expect to earn 50 tickets. And maybe this would be $50 if this was a casino. Maybe we only have to pay $10 for the operator and $10 for the space, and maybe we would win a profit. Who knows?